Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we will continue our projectile motion equation or projectile motion equation description, and with some examples. So the example that we have is the problem is, again we look at the same projectile motion, this time taking into effect the centrifugal motion of the earth, sorry, the Coriolis effect of the earth, right? Omega cross V effect. So the problem says a lead ball, this is the same experiment that was originally repeated by Galileo, who was measuring the impact of the earth's rotation on the weight. So the problem says, the experiment says a lead ball is dropped from the top of tower of Pisa, show that its path from that of a plumb line or vertical line show that its path deviates from that of the vertical line, and the question says is where does it land, or how much is the horizontal movement of the motion of this lead ball. So where does it land? Okay. So of course the only force acting on the on this lead ball is its weight. So we can write down the equation of motion straight away. So we have that dv dt plus 2 omega cross v, this is the Coriolis effect, this is equal to minus gk, k being the minus k being the vertical axis downward. Okay, so then what have we got? So we can integrate this. So we can integrate this. We can integrate this equation of motion. So at t equal to 0, v is equal to r is equal to 0, right? So what we get is that dr dt plus 2 omega cross r is minus gtk, right? We have integrated this, let's say equation number a, and we get plus a constant of motion, and we can further use our initial condition at t equal to 0, the velocities and the position is 0. Let's say the position at the top, the base position is our starting position, and we drop the value c. And now what we have is, we can further integrate this equation. So further, let us call this b. So we integrate equation b, and we see that r of t is minus half, again we are integrating half gt square k minus 2 omega cross r t prime dt prime. So here this is the integral term here. So this is from 0 to t. Now suppose we did not take into account the Earth's rotation, we see that the Coriolis, without the Coriolis effect, the final the final projectile motion is quite simple to understand, that this is a parabolic path. But now due to the Coriolis effect, we have this next integral term which we have to evaluate. So this question comes is, let us call this equation c. This question comes is how to finally evaluate c and remove the integral. So we can remove this integral in c by using a perturbative technique. So we can use inside the integral we can use a leading order approximation of the position and integrate out this integral and find the eventual answer. So let us say, so we solve C using zeroth order approximation R0 corresponding to omega equal to 0, right? So we solve C using 0th order approximation corresponding to omega equal to 0, and then if omega is 0, then our R0 from here, our R0 is minus half gt square k, right? So that is when omega is 0, this term is dropped. So this is this quantity. Okay. So now we are going to use the 0th order approximation in this. Integral. So what is the whole logic behind this? We are saying that omega, capital omega is the Earth's rotation, and the Earth's rotation magnitude is typically small compared to whatever is happening in the moving frame. Right? We saw that the magnitude of omega, capital omega, is 10 to the power minus 5 radians per second. So this is already in lower than the leading order. At least it is very small. So we have used the approximation omega equal to 0 to quickly find the answer to the leading order. Now we use this result to put it in the integral, and now our first order approximation R1 comes out to be the leading order approximation R0. So this is equal to minus half gt square k minus 2 omega cross integral 0 to t R0 of t prime dt prime, right? So this is equal to, now we are going to we are going to use the result. What is R0? So this is going to be the first leading order, half gt square k, and now we integrate this using the leading order approximation. This becomes plus 1/3 gt cube, and R0 of t is omega cross with k. Omega cross with k. Okay, so omega was sitting here outside, and R0 was a vector pointing in the k direction, and the minus is absorbed. So here we are. So then we know that the Earth's rotation, we have to go back to this diagram where we were looking at the object's motion, and we have to consider this angle beta now. Beta is related to the latitude angle. So we are going to rewrite our omega in this with respect to this angle beta. So omega is minus sine of beta I hat plus cos of beta k hat, right? So now omega vector, we look at, again I have to go back and show you the diagram, but the listeners can right away refer to the diagram that I was just referring to. If we look at with respect to the north-south axis, now this is omega. So omega, this is the magnitude of the angular velocity of the Earth. So now we are so this is the angular velocity of the Earth's angular velocity, and this is the axis of the moving frame. So this is our frame F prime. So in F prime, this is what the angular velocity looks like. We club it into this vector relation and find out the result. We see that up to first order approximation R1 comes out to be minus half gt square k bar plus 1/3 gt cube omega sine beta j, right? So that is what we have, and this is our new position, which is which is in addition to the old position. Okay, so which means that this new quantity is the net horizontal movement of the object from the vertical, right? The vertical distance traveled is this quantity, and the horizontal displacement due to the Earth's rotation is this second term. And this we call it as the drift due to the motion of the Earth, right? And the drift now is, so now to calculate this drift, to find this drift, what we see is that we have to find the total travel time of the ball, the total time. The total time, we see that the total time tau is coming from here. So let us say the total distance traveled is h. The total distance from the point which is where it is thrown is h, right? H. And total time taken is 2h by g, 2h by g, that is from the regular projectile motion, this being the total distance traveled. From here we can find the total time approximately. And now if we plug it into this drift formula, we see, let us call this as d. So d is 1/3 g tau cube omega sine beta. Omega sine beta. And we club this into this formula. We see that this is also equal to 8h cube by 9g after clubbing everything, omega sine beta. Now if we plug in some numbers, so let us say for 50 meter drop, this is our value of h, and let us say at latitude 44 degrees north, so this is equal to beta is 46 degrees, right? So beta is 90 minus theta, so this is 46 degrees. And we see that if we plug all these quantities, our drift comes out to be 5.6 millimeter, right? So of course, because of the rotation of the Earth is so small, the drift is appreciably low, right? And now I just want to highlight the fact that these types of experiments, which is used to calculate the drift of the motion due to the Earth's rotation, is the so-called Foucault's pendulum. Now there is, to all the interested listeners, I just want to highlight that Foucault's pendulum was developed in the early 1600s to observe this phenomena of the Earth's rotation. Recall that when Galileo was doing his experiments, there was this general consensus that Earth was not flat. And then there is an original setup which is kept in Pantheon in Paris, which is measuring the motion of this, which is measuring the rotation of the Earth, right? So listeners who can do a Wikipedia search will directly go into this experiment which is kept in Pantheon. And so let us now look one example related to this Foucault's pendulum. So the problem is Foucault's pendulum, right? So the problem says so the idea should be clear. We have a pendulum which is of course oscillating, and in a regular fixed frame the oscillation of the pendulum should have been in 2D, should have been on a plane, should have been a planar motion, but due to the Earth's rotation, the rotational the plane of oscillation will also rotate with the rotation of the Earth. So the actual motion of the object, with taking into account the Earth's motion, the actual motion of pendulum is a 3D motion. So the question says, how does the Earth rotates, rotation affect small oscillations of an ordinary pendulum. Okay. So the question is, so again, let us now look at the motion of the pendulum, the equation of motion. So we have m dv dt plus 2 omega cross v, and this is equal to minus mgk plus t, and we see that Well, so this is the pendulum, and the pendulum has a weight. So this is the weight of the pendulum. Let us denote it along the k-axis. So that is the weight. And there is also the tension in the string. So that is denoted by this vector t. So then what we have is that of course the pendulum is the axis of rotation, the axis where we are talking, the motion of the pendulum is happening is this quantity x y z, and we know that due to the Earth's rotation the object is also rotating. So we have x prime and we have y prime. So the pendulum is also rotating, right? Let me call this center as O. And now this question is, we have to solve this equation of motion. So we see that, so let us see now in the 0th order. So at the 0th order, which means what do we mean by 0th order? When there is no acceleration, or there are no net forces, or there is no Coriolis effect of the Earth, then we expect that the tension in the string is balancing the weight of the mass. So this is at equilibrium. At equilibrium, we see that T is equal to mgk. Right? So this is at equilibrium. So now we have further what we have is that R is A, and we see that this is the motion of the object in 3D. So the object in 3D will have a position vector R, right? So we expect that with respect to we expect that the position vector of this pendulum with respect to a fixed frame with respect to the support is R, and the total distance or the magnitude of R is constant, which is A, because that is the length of the string. So A is going to be x square plus y square plus z square. Notice that we are looking at the general 3D motion, or we see that we can now rewrite z. Z is equal to a square minus x square plus y square, and we see that also this is equal to a 1 minus x square plus y square by 2a, right? We see that this is the case. Okay, so then delta. So this question now is, what is the change in the coordinate plane, right? So or what is the change in the third dimension, that is delta z, or how much is the change in the planar motion? So we see that if we were to find delta z, we see that delta z will depend on, z it depends on x square and y square. So the change in the third dimension delta z will depend on order delta x square and order delta y square, right? And now what we have is that it can be shown that these are, so we expect that because the changes in the third dimension is second order, we expect that dvz dt, the velocity or the acceleration in the third dimension will be second order quantities, will be second order. So this is order delta square. So whatever this delta refers to, this is second order quantities. Okay. So then what we have is that, so which means that if we were to write now the equation of motion, if we go back and look at this equation of motion, that dv h dt plus 2 omega cos beta k cross vh. So dvh dt 2 omega cross beta k cross vh plus G by A RH, this is equal to 0. Right? So we have just looked at, so we have neglected the effect of the third dimension, and we have now looked at this equation of motion completely in the horizontal, the plane of the motion of the pendulum, the horizontal 2D plane. So hence we denote the velocity as VH. So VH means horizontal velocity. Horizontal velocity means velocity in the plane, in the XZ plane. Sorry, yes, in the XZ plane. Horizontal plane, the effect of the third dimension is neglected. So what we have is, so what have we got? So this quantity here is, so this is 0. So, right. So this is, these are the different quantities. This is set equal to 0 here. There is no effect of string tension because T is mgk. This is at equilibrium. So this is what we have, right? So now, if we were to, so what we have is this RH, because this is in 2 dimension, this is equal to xi plus yj, and my VH is Vxi plus Vyj, right? So these are all in the XY frame. So now if we now shift to our, so if we look at this equation now in the rotating frame or in the precessing frame of the pendulum, so in frame F prime, what we see is, let me call this equation as equation number 2, right? Equation number 2. So in equation number 2, what we see is that d2RH dt2 plus, we see that in the rotating frame we have minus 2 omega cos beta square. This is RH. This is equal to 0. So how did we get that? We see that we have looked at, we also have this G by A. So this is plus G by A. So RH. So this is in the 2D motion. So this is only in the plane. So this is the scalar equation. Now notice that this is very similar to the simple harmonic motion, but now with frequency omega equal to n square minus this 2 omega cos beta whole square, right? And where my n is square root G by A. My n is square root G by A. Okay, so then I think we are all out of time here, and in the next in the next module we will wrap up this discussion on this. This example is over, and in the next module we will introduce another brief discussion of of an example of these objects in so the so-called objects in air, moving in air, winds and air currents, the so-called geostrophic effect, and we will wrap this discussion on the moving frame. So thank you so far for listening.